Space Research, Moscow, Russia. Professor Elina's expertise is in theoretical physics in the field of theory of critical phenomena. She has contributed to the understanding of critical transitions with the new theory of nonlinear saturation of pre-bifurcation noise amplification and the rise of the correlation time. Obtained theoretical findings gave rise to a series of new results in different fields, such as cardiac dynamics, liquid crystals dynamics, climate dynamics, and monsoon forecasting. As a part of the International Climate Initiative, Professor Elina leads the group on Indian monsoon forecasting. We're very glad you could join us today, Professor Elina. And a small note to the participants, please use the Q&A to enter your questions and do upvote questions that interest you so that the moderator can prioritize them later on. Over to you, Professor Sayan.
Thank you, Ruchi. I'll just try to share the screen. Is it visible?
Yes, you can go ahead. We can see it.
Yeah. Hello, everyone. So I am Sayan Gupta. I'm going to speak about this initiative of ours, of complex systems and dynamics. Before I do that, I would just like to make a brief introduction about where we are. We are in IIT Madras in Chennai, which is in the southern part of the country. And it's it's the fourth largest city of India with a population of about 7.5 million. And what is not usually said is that it has a very long beach and a very beautiful beach. So if you are interested in all this, Chennai is the place to come. Also, we are in a IIT Madras campus, is lush green, very beautiful. And it was earlier a part of the Guindy National Park, and it has lots of nice flowers, flora and fauna. So it's, I hope these pictures will entice you to come and visit us. Okay, going back to the research aspect of complex dynamical systems. So when we are dealing with very complicated systems like the human brain, which is made up of billions of neurons, or we are talking about the ocean atmosphere coupling, like on planetary scale, or we are talking about social dynamics like shoals of fish, flocks of birds, epidemics, biomimetic flows, and dynamics and active flows. So if you're analyzing, or if you're interested in studying these systems, the traditional reductionist approaches that we adopt in science and engineering are not really suitable for analyzing the collective behavior. So it is where this complex systems comes into the picture, where we marry the fundamental principles of the physics of the system, coupled with the empirical observations and experimental data. And now with the advent of technology, we have the ability to collect voluminous amount of data. So all these, when we together couple each other and form what is the new approach to the analysis of these systems. So this is an emerging interdisciplinary field, and this is what complex dynamical systems is all about. And we are interested in the dynamics of this type of complex systems. So this is as you can well imagine, this involves an interdisciplinary approach to the research. And as a group, we have been, informally, we have been in existence since 2017. And my seniors tell me that in some other form, there was another group about 10, 15 years back in the physics department. But this group now has taken a much more structured shape very recently. And in here we have, I'll just introduce my colleagues. We have Nilima here, who's a emeritus professor in physics department. We have Srinivas, who is in biotechnology. His areas of interest is in computational neuroscience. Then we have Srinetra from aerospace engineering. Her interest is in biomimetic flows, fluid structure interaction. Mahesh is from applied mechanics department, interested in pulmonary fluid dynamics, aerosol and atomization. Anubhav is again a colleague from applied mechanics with an interest in complex fluids, geophysical fluid dynamics. Sumesh is from chemical engineering with interest in soft and active matter, complex fluids. Arun is from chemical engineering. He's an expert in causal networks, process control, data analytics. And of course, this is my my research interest is in stochastic dynamical systems. Apart from this, we have a very group of eminent researchers from all over the world who are our collaborators. We have Professor Kutz from Potsdam Institute for Climate Impact Research in Germany. Madhav is from Biocomplexity Institute, Virginia. Elena, who is the moderator today, is again from Potsdam Institute in Germany. Henning is from Virginia Tech, USA. Didier is from CNRS, France. Murlid is from Temsec Lab, National University of Singapore. Gabriel is from University of Buenos Aires in Argentina. Srinivas is from Georgia Tech. Anna is again from University of Buenos Aires in Argentina. Aravind Srinivasan is from University of Maryland. Arup is from Northeastern University. Wusuk is from Stockholm University. Jiangxi is from Rensselaer Polytechnic. Kirti is from Biological Systems Engineering in Washington University. Sarah is from Freie University Berlin, also from Global Climate Forum. Vivek is from University of Miami, USA. Zoltan is from University of Notre Dame. And Biao is from University of Alberta, Canada. And we have Udit from India, from Civil Engineering and IIT Gandhinagar. So together, this team, as you can well see, that encompasses a broad areas of, they have a broad expertise in different research areas. And we hope to all come together and solve some interesting problems over the next few years. What we are looking through the international collaborations is essentially some joint research through joint mentoring of PhDs and postdocs. We intend to have regular seminars. In fact, we have been having seminars off and on in an informal way since 2017, but now we want to regularize that, organize some thematic schools and workshops, two of which I'm going to announce today at the end of this presentation, short-term courses. We want to host international experts as visiting faculty. And this is also a very innovative thing that has been started by IIT Madras. This is, we are looking to recruit recent doctoral graduates who are on tenure track positions for full-time faculty. And this is open for non-Indian citizens and non-OCI. Under this umbrella, we are planning to recruit at least 2 young international faculty. So with this, I will hand over to my colleague Nilima to take you through some of the trust research directions, which is the aim of this center, and some of the research projects that are ongoing.
Yeah, you can hear me, right?
Yes, yes. Go on, Nilima.
Yeah. So, okay, my net has gone, in fact, and I'm on the phone. So let's hope for the best. Just warning you. Okay. So could you advance the page? Right. So in fact, Sayan said this right at the beginning, that what this center plans to do is to, in fact, study complex dynamical systems. And here on this slide, we have examples of a number of complex dynamical systems. For example, coupled neurons in brains, social dynamics in epidemics, biomimetic flows and dynamics, active flows. And we have members of the group who work on all this. Okay. And a very important direction, which we hope this initiative will be able to, research direction, which we hope this initiative will be able to take up seriously, is data-driven dynamics. For example, things like climate dynamics and ocean atmospheric coupling. Okay. So we'll be saying a little more about this, about our research programs shortly. Right now, can we go to the next slide, Sam? Yeah. So what is the idea? The idea is that reductionist approaches, I mean, for those who are unfamiliar with this, reductionist approaches are very unsuitable for modeling collective behavior. Okay. And that is because collections of individual entities, with evolving individual entities which are coupled together, can behave in a way which is very different from the way in which single entities behave. Okay? And this is so the study of such systems, like Sayan has said, is an emerging interdisciplinary field, and it can be attacked from various angles. So one thing is, one should understand how these systems behave. There are so many systems which behave like this, as you saw from the examples on the previous slide. And there is voluminous data which is available. For example, the climate system in which Professor Elena, who's the moderator today, works on, actually can in fact be modeled in ways in which we use the techniques of complex systems as well as complex networks. Yeah, next slide. Okay, so here is a little bit about complex networks. So as far as complex networks are concerned, now we are all familiar with regular networks. For example, a regular lattice, for example, the kind of lattices we study in solid state physics are in fact regular lattices, where in fact the neighborhoods are connected in a simple way. If we look at complex networks, then in the case of complex networks, the neighborhoods are not really connected in a simple way. And secondly, you can model many kinds of systems by complex networks. Okay? For example, to take the example which is on the top of everybody's.
Lost Nilima.
Can you hear me?
Yeah, we can.
You can? You can hear me?
Yeah.
So to take the example which is on top of everybody's mind this year, namely epidemic spread, the spread of epidemics on human networks or on, in fact, biological networks, but the networks of biological populations can always be modeled by a complex networks. There are social networks which in fact can be modeled by, complex networks. An example of this, am I audible?
Yes, ma'am.
Okay, because I have lost the screen, but okay, it doesn't matter. So the thing is that there are sociological networks, there are social networks which can all be modeled by complex networks. Plus, in addition to this, like we said in the case of epidemic spread, there are in fact processes where in fact there are processes which can occur with the network, with the complex network as a substrate. Okay? And in fact, Professor Bosa Tadic, who's here right now, and I have long been involved in studying processes on dynamic networks. Bosa, maybe you could say 2 minutes about the kind of work which we have been doing. Spend 2 minutes on it. Yeah. I was planning to ask you later, but the way my net is going, this is the best time.
Myself, okay. It's interesting how Nilima involved me in this without telling me in advance to prepare anything. But of course she could tell also because we worked for a few years together. And currently very interesting subjects is dynamics on simplicial complexes. And we also involved in that. And the major idea is that most of these complex systems have that can be represented by networks actually have hidden geometry, which goes beyond pairwise connections, which is called network. And they can be recognized mathematically as simplicial complexes. So we recognize them in many networks, starting from the brain, let's say, as a most interesting system, complex systems, but also in social and many other areas, in material science as well. So interesting thing is that the simplexes, these are, for instance, aggregates of cliques, triangles, tetrahedrons, and so on in different ways. They aggregated, mathematically precisely defined. So they actually can house interactions which are beyond pair-based interaction, like interaction on a triangle, 4-point interaction on a 4-click, and so on and so on. And in general, many body interactions which cannot be reduced to pair-based interactions, okay? So these are new concepts in the dynamics of complex systems, which probably are the trace new ways, new paths towards understanding why such complex systems like brain, for instance, are functioning precisely and stably, having so many connections inside brain regions recognized as nodes of the network and so on. So dynamical phenomena on these networks, this type of mathematical structures, known as simplicial complexes or hyper networks in more general terms, are now cutting edge of science of complexity. So I think, I don't know if Nelima wants me more, but I think this is just what do you say?
That was nice, but I think people might have questions later, which
okay. All right, thank you.
But that will take a while.
The opportunity.
And thank you so much for doing this.
All right,
off the top of your head. And yeah, can we go back, Sayan? I mean, or to the next slide. The next one. Yeah. So basically, I don't want to go into details of networks at this point. What I want to say is that there are many important systems. I want to go to actually. So what we said was evolving dynamical processes. Then we said complex networks. And what I would like to next emphasize is what is the contribution of data which can actually help us construct things like networks. Okay. So there is a very important difference in which actually complex systems have been studied in the past and the way in which complex systems have been studied can be studied in the last few years. Namely, there is now huge data available, which was not available in earlier years. Okay. So in fact, this huge data can be put to use or can be analyzed in many ways, and that enables us to analyze systems as well as find applications which in fact did not exist in the past. Okay? Like for example, to look at the kinds of examples which we have been looking at, you can use the huge amount of data which is available about climates to construct climate networks, and they can use to predict things about the climate. Okay? There's a huge amount of data which is available about, let's say, financial networks or networks of banks, which can be put to use to, in fact, find information about the way in which the directions in which the stock market will evolve, or for that matter, catastrophic events like financial crashes. And as you can see, the knowledge or the prediction or even the analysis of such events can have very important economic and ecological consequences. So this is the third angle from which at least we have envisaged that we can actually study complex networks. Okay, so the three heads which we are looking at is dynamics, then networks, and the third thing is data. And we'll be saying more. In fact, my colleagues will be saying more about each one of these three angles. Okay. There's an important thing which we have been doing in the context of this research initiative, and one of our oldest ideas which we finally put into action this year was to actually construct a degree program, an interdisciplinary degree program on complex systems and dynamics. Okay. I think we said this in the beginning, Sayan emphasized this in the beginning, is that this is a huge intra-departmental effort. Okay. So in fact, as you probably saw in the, we'll skip the ongoing research projects, Sayan, just go to the IIID. Yeah. where in fact we have set up an interdisciplinary. So this is a very new area. This is a very new area. Complex systems and dynamics programs do exist in other countries, but to the best of our knowledge in India, this is the first degree program, and the other programs which we have also exist in other countries are not very old. Okay, so this is a new direction, and we thought that we have exactly the right combinations of students who can actually benefit by this kind of program, who would be interested both in what are the universal features of the kind of systems that we are looking at, as well as in the kind of applications that such systems can be put to. Okay, so can I have the next slide, Sam? Yeah. So what are the program objectives? And I should say that it's Sayan who was crucial in putting together the entire structure of this. This is to train students in the mathematical modeling of complex dynamical systems, to build networks from models of data, to analyze the systems using theories of networks, nonlinear dynamics, stochastic dynamics, and in these modern times, and that also in the context of IIT, which is exactly suited to doing this, data analysis and machine learning. Okay? So data science techniques are extremely important for this. Okay? High performance computing, for which we have a major center, okay, and hands-on experience through projects. Okay. Just one more slide. The next slide, please. Okay. So we have set this program, which has there is a curriculum which has a core of 30 credits. You can essentially take courses from 3 core baskets, which is networks, nonlinear dynamics, mathematics and numerical analysis. Okay. And there's a certain number of courses which have been set as compulsorily for from each one of these core baskets. Okay. We have something like, we have a huge collection of about 45 electives, which is available due to the fact that we really belong to 8 or 9 departments. Okay. And again, we can accommodate a very large number of projects. We have given, because of the kind of program that we have given heavy emphasis to the project. So there'll be something like 85 projects. When we start telling you about the kind of research projects we are working on, then in fact, we know that we will be able to tell you what kind of projects we are in a position to offer people. And this is a total program of about 160 credits. It is hoped that the students who emerge from this program will have a variety of options. I'll just show you what the curriculum looks like. The next slide, please, Sayan. Okay. So here is the first core basket. Here is the second core basket. Can we see the next one? Yeah. This is the mathematics basket. And the electives, not that anybody can read it, but just to show you how many possible electives are there. Okay. And they go all the way from mathematical physics to the hydrodynamics of complex fluids, about which my colleagues will be talking, the data-driven modeling of process systems, etc. Now, where can the applications of these systems be found? And the applications of these systems can actually be found, as we said, here is this list. Like I started off with climate science, where in fact, we have done some stuff which is related to predictions. We have a joint project with Professor Elena, which is actually related to climate science. And we hope that there'll be students who will be joining on this project. Some of my colleagues work on computational neuroscience. There's machine learning in fluid dynamics. As we said earlier, biomimetic flows. There's complex flow and physics of living matter, urban climate modeling, science own work on stochastic dynamics, the dynamics of social behavior. And again, I repeat, who needs to, at this point, needs to be reminded of the importance of epidemic modeling. So these are in fact possible research areas on which there are current projects, and in fact on which there are current problems. There are also possible industry applications. You can actually have applications of these to, for example, financial systems, plus geophysical systems, as we earlier said, climate systems. And as far as industry applications are concerned, I'll leave this to my colleague, Professor Mahesh, who is in a better position to tell you about it than I am. So could you, Sayan, could I hand over back to you?
Yeah, thanks, Mahesh.
Yeah.
Good afternoon. This center is very clearly positioned at the cusp of science and engineering. Many of us are faculty in the schools of engineering, but interested in developing science-informed solutions to complex problems. So the core approach is to develop a deeper understanding of the set of problems that Nilima talked about and Shayan mentioned, and to help industry and society at large benefit from the understanding that is developed from an analysis of this problem. The problems themselves are very application motivated. And that's one of the, I feel, the distinguishing features of our approach to selecting the problems. Shayan, next slide. So just to highlight some of the application areas of emphasis, climate science, as Nilima mentioned, there is a large group of banking and insurance that is currently not aware or not sure how to model long-term climate change related risk into their modeling. So the science that we develop as part of these projects would help that group of stakeholders make better decisions. Neuroscience is an area that doesn't require much description. Brain-inspired computing is an application that's looming on the horizon. Biological systems, understanding how biological systems operate and self-organize is of interest to many different applications, including polymer thin films, particulate coatings. There are many different examples in engineered systems where self-organization plays a role. Again, we don't have to dwell much on the multi-physics systems and active flows. They are part of pretty much any smart engineered system these days is a multi-physics system. So a complex systems approach would help the cause a great deal. Again, the last one doesn't require much introduction. The financial markets, all of us are embedded in them. And understanding the dynamics of financial markets and social networks from a complex network viewpoint would certainly help banking, insurance, and the regulators make better decisions. So that's the core approach with bringing on industry partners. We have a small group of industry partners that have already signed on. We expect a larger number to come on, and we expect to bring these partners on through three different sort of approaches. One is to form an industry consortium, which would have members of the consortium would have visibility into the work being done in the center. The second is where a particular industry partner may be interested in working with a small group of researchers on a very clearly identified project. That's a second mode of interaction. The third is through workshops like this, which would be periodically conducted, where industry partners would be brought on board to first be made aware and for us to learn from them as to what the emerging problems are as well. So for example, Climate Policy Initiative is a think tank that helps governments understand climate change and factoring climate change into their thinking, into government's thinking broadly. So we hope to partner with them and extract and learn from their domain expertise in doing a better job of modeling, of positioning our solutions to be of use to them. So that's our approach with industry partnerships. Back to you, Shayan.
Yeah, thanks, Mahesh. I would now like to go back to the research problems that we are currently working on, just to give an overview of the type of problems that currently we are working on. So I'll just quickly go through, and if you have questions, we have all our collaborators here, so they can answer questions. So one aspect is machine learning in complex flow fields. This is being done by Professor Sunetra Sarkar. So here I will just skip through quickly because we are running out of time. And this is also biomimetic flows. Again, this is an area which is being led by Professor Sunetra Sarkar from aerospace. Then we have skew analysis of networks, symplectic networks. I think this is led by Professor Nilima. Then climate dynamics. Yeah,
actually,
Nilima, you want to say something?
Yeah, Professor Bosa, in fact, was referring to exactly this. Yeah, so we've already said a little bit about it. Yeah. Okay. Yeah, go on.
Okay. Yeah, this is again climate dynamics. This is again Nilima's area of work. So I think you have already mentioned.
I've already
said
that.
About it, Nilima, right? Okay.
We did a little bit of prediction on El Nino, La Nina, and let's see where it goes. You could skip this.
Yeah, this is an initiative that is led by Professor Srinivas Chakravarti from biotechnology. He's around here. So if we have any questions, we can come back to this later stage. So this is about bird songs. I think this is also, again, Nilima is involved in this work.
You could skip that also. We did various kinds of data analysis of this, but you could go on. Proceed, please.
Yeah, this is something that I work on, noise-induced transitions. So it is how noise affects the dynamics of nonlinear systems and how the bifurcation behaviors are changed, and it leads to noise-induced intermittency, basin hopping, and many other very interesting phenomena, which has important implications in both engineering as well as even in systems like climate. And yeah, noise-induced transitions is also, this is something that I am trying to work, and these are some new areas that I'm trying to work in. We had some other problems here. Yeah, causal discovery of complex systems. I think this is something that is led by Arun from chemical engineering. How then active flows. This is something that is led by Anubhav and Sumesh. And Mahesh also works on something related to pulmonary efficiency of pulmonary, how sprays and droplets can be influence the pulmonary infections and so on. So I think these are the main areas of the problems that we are currently working on. So maybe it is time to stop now because we are running out of time, and we have just enough time for taking a few questions, maybe. Over to you, Elena.
So it's very impressive.
I would just like to finish with one thing is that we have two workshops, one on August 14 to 16 on computational neuroscience, and another on August 25 to 28 on complex networks. And we are actively looking for hiring research scholars in MS, PhD through the regular departmental processes, as well as through the interdisciplinary research program, and postdocs through the IPDF, Institute Postdoctoral Fellowship Program, and also the YIF faculty positions. So we are, these are our website and email, and some of our past talks are also available in our YouTube channel, and all the subsequent seminars we are going to upload in this YouTube channel. Yes, I'm done. Elena, you can take over.
Okay, greetings from Potsdam, and I'm happy to be participate in such exciting seminar on complex systems. And by my experience, I can tell you that complex system needs transdisciplinary approach. And I found very impressive list of complex problems that address in your complex system center. And it's really very important for students to understand to find solutions for the problem. You need first background in physics and mathematics, and then To understand how system works, you need background in statistics and nonlinear dynamics. And then trying to predict something, you need machine learning and another data analysis techniques. So it's really multiple type of experience need to be able to solve problem in complex system. And so what, Sayam, we going now? Should we going to answer in question? Should I ask audience about questions?
Yes, maybe we can ask some questions. I mean, we can pick some questions.
There are questions and answers in the window. I can see 35 questions there.
Oh,
okay.
So if somebody will help me with, so I will look some questions.
Yeah, Richard, could you just tell her how to open, please?
For example,
just click on it, right?
So I see. For example, so it's I think it's difficult to take 36 questions, so I will just take randomly. So this question to me, okay. What are the parameters that one should look for climate modeling? So this is a very big topic. And for example, just to forecast monsoon, I use two parameters, not parameters, climate variables. First of all, nature of air temperature that's available by data in IMD actually data, and also in Stepan-Curry analysis data, and relative humidity. So these two climate variables allow me to forecast monsoon onset and withdrawal in central part of India, Telangana, and in Delhi this year. So you could find my forecast on web page on Potsdam Institute of Climate Impact Research. So the next question. Next question. You said for this complex system, reductional approach, I think it's to millima. Reductionist approach is not suitable. However, for active Brownian particles of self-propeller particles, example of collective behavior, don't we use the same reductionist approach via Langevin equation?
Yeah, but via the Langevin equation, they do interact with each other, right? And in fact, effects like swarming, etc., are an example of the fact that in fact, all of self-propulsion is a consequence of the kind of effects which the individual behavior of each particle has on the others. So in that sense, it is, I would not exactly call it a reductionist approach. The fact that each individual entity has its own way of motion is a separate issue. That happens in many ways. That happens in, it's always there in any kind of collective phenomena. Okay, I mean, okay, for the stochastic behavior, it works a little differently. And I think someone like Anubhav may be able to give you a better answer than me.
So the next question is, for example, where is the use of complex system and electrical engineering? This is a lot of use of complex system dynamics. So first of all, this is about power grid. So instability in power grid is very well-known phenomenon in IIT Madras, I think also. And there is a complex system and there needs transdisciplinary approach to take this problem, to solve this problem. So another question is, how to use network-based technique in real life? So as you can see, Professor Nilima used network-based approach to forecast, to predict El Nino. So this is a real life forecasting. So one group in our Potsdam Institute working on network-based analysis of power grid, how to construct better, connect better grid points to provide stability and of the whole network, and many other applications. For example, transport. For example, even medicine. So many applications of network in real life. And okay. How to collect data. So actually, you do not need to collect, it's possible, of course, to collect data for somehow, but currently there is a huge source of data around the world available for analysis. So as I told you, for example, in India, Indian Meteorological Department collects a lot of data, and many of them available for free to download from website and to analyze. It's a lot of data and NASA website. I use example NCEP and carry analysis data. So you could analyze every point of on the planet or globally. So it's really so huge data available and a lot of work for you and a lot of interesting problem you can solve using data analysis. So, and maybe some last question. So this is a question from students. Does this program is applicable only for IIT Madras students, or is possible for other students also? So Sayam or Nilima, please answer this question.
Yeah, as of now, this is only applicable for IIT Madras students, this dual degree program. But we are recruiting students for masters and PhD through the regular processes, as well as through the departmental, to the individual departments. Also, we are another modus operandi through the interdisciplinary research program. So all these details are available in our IITM website. I ask, please go and visit the website. All these details are available there. Thank you.
So thank you very much. And what should we go? Should we go to Sujit talk right now?
Richu, are we out of time now? Hi, Richu or Lisa?
Yes, Dr. Sain.
Formally, we have to end the session by now. But the session will be live. If you want to continue the discussion, you can carry on. But so the floor is open. So some of us will move to the other session. But if you would like to continue the session, you can.
You can take on more questions and answer the questions here, and the meeting can go on. We don't need to end it necessarily. We don't have a hard stop. So you could take on more questions.
Okay. The other session can go on parallelly, is it?
Yes,
okay.
that's right.
Yes.
Okay, fine. Yeah.
Okay. And then 2 more questions from students from chat, or should we ask our guests something? We have a guest, Ram Ramazwani, and then Professor Balakrishnan and Professor Bosa Tadic. Maybe we should
ask them for comments or
yes,
questions.
For comment or recommendation for students.
Yeah.
Yes, please. Yes, please, Bosa Tadic.
Okay. Okay, thank you. Sorry.
Okay.
Sorry. Can I speak now?
Yes, please.
Okay. I'm interested. It's very impressive, the program that you presented. And I actually recall how nice place you have there. I was there long ago. So thank you again for inviting me here to give me this opportunity to see all this even shortly. So I'm interested, if you have data in neuroscience, you mentioned that there is okay, one thing is brain-inspiring computation. I'm not an expert in that, but I'm interested in more like in this, real brain problems like diseases and this kind of things. Do you have data, or how you collect such data, and what kind of methods you plan to use to analyze them? So this is one question. Maybe somebody can answer or comment or just think about it. And the other one is very interesting. You mentioned epidemic modeling. I'm pretty much interested in that, and would be really glad if there are students who want to collaborate over, this distance with some professors there and me, including me. So, so you said there are data, there's machine learning, there's networks, but also I think you need to think of agent-based modeling as a dynamics, which is much closer to what's happening in these systems, right? So interestingly, nobody mentioned agent-based modeling, but it's one of the, nonlinear dynamics type of nonlinear dynamics modeling that that can reach everywhere, practically in all complex systems. So these are two points that I wanted to just stress once again, highlight, okay, to think about that. And if somebody has specific questions on this, I will be happy to answer because I have some experience in this. Thank you.
Thank you very much, Professor Bosa Tadic. And if somebody has a question, let me look in chat right now.
Elena.
Yes, please.
Hi.
I see the voice, but not able to see picture. Ram Ramazwani, please.
No. Okay, no, I mean, first of all, I'm sorry, I've been intermittently in and out of this meeting because of my poor connection here. But it's just phenomenal to see so many people involved in this complex systems, and especially the kind of directions that the IIT Madras group is taking. I mean, I think this is making a virtue out of necessity over here. We've got so many people from all over the world who are able to participate in this meeting. I think it's just a very good use of the situation, so to speak. One question or request that I have is because the IIT Madras is an institution which is, it's a technology institution, it would be really nice if the result of many of these studies would be in devices or in applications. I'm sure that people are thinking about it, but it would be really interesting to know what kind of practical applications, especially in the neural area, that people are thinking about. And, with a strong focus, I think a lot of very nice stuff can be done now. Okay, so with much good wishes and a lot of hope from this particular endeavor of yours. Okay, thank you very much.
Thank you, Ram Ramazwani. And if somebody have a question to Ram Ramazwani and Professor Bosa Tadic, and maybe Professor Balakrishnan would like to say some recommendations, suggestions for a student. Okay, and then maybe later, and then I will use I will read one more question. For example, how can this complex system can help in analyzing aerodynamic behavior of wind turbine blades? So very much. So it's possible to analyze dynamics, aerodynamics, this complex network. And actually next talk of Professor Sujit partially Professor Sujit also, if I know, use complex network analysis in turbulent combustor. So you could see example in the next talk. So should we go to the next talk now?
Yeah, sure. I think what I will suggest is many of you have asked questions here. Can you please email us these questions? And we will try to answer them separately through that way.
So this is a 70 question. So
yeah, there are a lot of questions. Yeah. So I think Professor Elena also needs to has some another meeting probably. So we'll just like to maybe close this session now here.
Yes, Professor, sure. Like we could send us the questions to you from our office list.
Okay, thank you.
Okay, thank you.
Thank you everyone for joining, and thanks Elena for joining, and Professor Boslika and Professor Ram Ramaswamy and others. Thank you very much for joining.
Thank you. Bye-bye.
Thank you. Thank you. Bye-bye. I have a question regarding Professor Sujit's talk. I thought it's the same seminar, no?
No, it's a different link. It's a different link.
It's a different thing. Yeah.
It's different. Okay, but it was a poster. Okay. And how should I reach there?
Yes, but this long-term effects is not quite.
So Professor Elena, you haven't received the Zoom link for that webinar?
For another one. So it will be another seminar.
Yeah.
Please send me again. Please send me again. Send me link for another also.
Okay, we'll send you.
Because I promised Professor Sujit to be actually a co-author of this study. And I really very interesting to see what's going on.
Sure, I'll send it to you, Professor, right away.
Thank you very much. Thank you very much. And Sayan, so I just was wondering that it's going longer, but everything is, so we accomplished our goal, isn't it?
Yeah.
Okay.
Thank you.
So, so thank you very much for all participants for this very exciting and maybe stimulating seminar. So, you know, now you know a lot about possibility to use complex system in different fields of research. And it's really exciting. I promise you, let me say, very busy life, not easy life to do research, but very, very interesting. Very, very interesting in different aspects. I worked in topic in medicine, for example, cardiodynamics. I work on liquid crystal dynamics. Now I'm working in climate and everywhere. Expertise in complex system, now linear dynamics. All this helped me in different directions. And it's really very, very interesting. I wish you good luck with your choice of your research topic.
Thank you. We have a very big team here, and I think all of us are quite excited about working in this under this umbrella. So we look forward to having a lot more interactions in the next couple of years. Thank you very much.
And we hope to see you physically here as soon as possible.
I also
we've been waiting for the last 2 years. I mean, it's been, yeah. Okay. So I think Bosa has gone. Okay, I'll say bye to her separately. So bye everybody. Thank you, Sayan. And thank you, Ritu and Yuri. And thanks to all our colleagues.
Thank you very much. Bye-bye. Bye-bye.
Bye.
Thank you, everyone. So we'll end this now. Thank you.